Kirkwood Math. All right, welcome ladies and gentlemen to topic 4, lesson 2. We are going to go ahead and learn how to solve these systems of linear equations using substitution. So we are building our math toolbox, our kind of figurative little toolbox that we have that we can reach in and pull out various types of methods to solve problems. Depending upon the situation, certain tools will be better. So last time we learned how to graph. Now we're going to learn how to do substitution. This is going to be more accurate because graphing is more of an estimation, but yeah, let's get to it. So we are on page 80 and 81 of your student companion. So right here, we're going to solve the solution here for this system of equations. When you use substitution, it is super handy to have one of those equations where the variable is solved. It doesn't matter if it's y or x, but if this variable right here, if it's isolated already, then substitution is really easy to use. If you are trying to use substitution and a formula or an equation is not isolated, you'll just have to rearrange it so that it is isolated, and we'll show you an example of that. Okay, so in this one right here, and again, remember to write down your steps in the corner of your book. The first step you're going to do for solving with substitution is getting an equation solved for y or x. This first equation is already solved, so we're just going to substitute. Because y is the same as 6x plus 7, I can take the 6x plus 7. Oh, hold on. Sorry. I can take 6x plus 7, and I can just replace y. I'm just going to go ahead and put it right in for this variable. So you can see that down here, where they just took y, and instead of y, they wrote 6x plus 7. Once they've done that, they're going to go ahead, and step 2 is to now solve for x. So they are distributing their minus 8. They are combining like terms to combine those x's here. They are then doing the inverse operation of addition to add the 56 to 4, and then the inverse operation of division to divide by negative 45, and then simplify or reduce to get x equals negative 4/3. My next step here, because I know what x is, I now need to substitute x into one of the equations. It can be either equation, so you can see in this example that they go and they use the other equation. They do that because it is easier for us to solve for y when our formula is already set up to solve for y. I could put my x value in this equation, but you can see that would be a lot more steps and take a lot more time. So it doesn't matter which equation you do, just whatever one's easiest. So they went ahead and substituted the negative 4/3 for x. They multiplied that out, added the 7, and they got that y is negative 1. So this system of equations has exactly one solution, and that solution is negative 4/3 and minus 1. The last thing that we're going to do is what all good mathematicians do and check our work. You can save yourself a lot of pain and a lot of trouble by just checking your work. So we're going to go ahead and replace the y and x that we received when solving our problem into both equations. If both equations turn out true and have a true equal result, then we know that we are good to go. All right, so on page 80 there, you're going to go ahead and try using substitution yourself. You can see here that on this first problem, x is solved for us already. So go ahead and just use the value of x. Just take this and replace it right here for x instead, and then solve. Once you have that answer, plug it into one of the equations and solve for y, and then check your work. And you're going to do the same for b down here as well. All right, now we're really going to kind of compare graphing and substitution methods to really see kind of why we would use one versus the other, and kind of why the substitution method is a little bit better than graphing because of how precise it can be. So our problem is a vacation resort offers surfing lessons and parasailing. If a person takes a surfing lesson and goes parasailing, she will pay a total of $175. On Friday, the resort collects a total of $3,101 for activities. How much does each activity cost? So in the picture, I know that 16 people went parasailing and 20 people take surfing lessons. This is how they got their equations here. So they went ahead and made X equals surfing lessons and Y equal parasailing lessons. So if you take one parasailing and one surfing lesson, it costs $175. If 20 people go surfing and 16 people go parasailing, that makes $3,101. So that's how they got the equations from the word problem, very similar to what we're doing in our warm-up this week. Okay. Here are our two methods. So from what you can see here, they actually used a graphing calculator to graph these lines, and that's how they got the very precise answers of 75 and 25/100ths and 99 and 75/100ths. If you were doing this by hand and on paper, you probably would have rounded this to just 75 and rounded this to just 100. This is one of those reasons why graphing is not super precise. Okay. The one positive that graphing has, though, is that you get to do less math. Once you graph your points, you just have to check your work and see if they check out, and then you have your answers here. In method 2, using substitution, we have way more math to do, but the benefit is I am going to get an exact answer even without a graphing calculator. So step 1, again, these are really good steps to write down. The step 1, whenever using substitution, is always solve for one of the equations for either x or y if the equation isn't already solved. So here I had x plus y. I'm going to take this one because it's really easy for me to just subtract one of the variables, and now I have an equation that's solved. The second step that we're going to do is then substitute the x and solve for y. So again, I know that x is the same as 175 take away y, so we're just going to go ahead and replace that in x in the other equation. Once we do that, you're using parentheses here to distinguish and multiply. We're going to distribute across, we're going to combine like terms, and we're going to solve. This way, I can get 99.75 and be very precise in my answers. My third step is then going to be, once I have one of my variables solved, I then need to substitute that variable in one of the equations, whatever is easiest, so that I can solve for the other variable. So in this case, I'm substituting y, and I'm going to solve for x. And then my very last thing is then to check my work, because good mathematicians check their work. So again, as you can see, method 1, really good for estimating, really good if you have a graphing calculator, less math needing to be done by hand. Method 2, estimating, super handy when one of the variables is already solved, and you can get very precise answers without a graphing calculator. Okay, go ahead and practice what we just did. You may pick what method you want to use, if you want to graph or if you want to solve using substitution, but you will have to write the two equations from the word problem just like we're doing in our warm-ups. Moving on over to page 81 in your student companion, we're now looking and comparing systems with many solutions or no solutions. It works the same way as graphing, but instead of looking at lines and slope, we're going to be looking at the solutions. So here we're going to substitute y. We're going to solve just like we did before. When your answer has an identity, so if you remember, you guys were talking about how this is a mirror. So when this side is the same as this side, or when it's a true statement, then you know that you have infinitely many solutions. When you solve a system of equations and you do not get a true answer, so down here, 4 does not equal -4. So when this is false, then you have no solution. And again, this is very similar to any of those one, none, or infinitely many problems we've done in the past. We're just using two equations to solve this time. So go ahead and give those a try. See if you can solve these two systems of equations and tell me if they are one, none, or infinitely many solutions. You can also challenge yourself to see if you can figure it out without using substitution, although substitution is the focus that we are, the tool that we are focusing on right now, so it would be really good for you to practice that as well. All right, example 4 is just kind of modeling real life situations. So we're going to look at a real life example here. We have Nate starts a lawn mowing business. In his business, he has expenses and revenue. Nate's expenses are the cost of the lawnmower and the gas, and his revenue is $25 per lawn. At what point will Nate's revenue exceed his expenses? This is expenses. This is a really common real world problem that all business owners and creators have, because it takes money to make a business, and there is a point in time where you will make more money than it costs to start. So let's figure out Nate's. So the very first thing we have to do is write those equations. We're pulling them from the word problem and from the picture here. So Nate's expenses are going to be, they're letting Y represent the dollar amount of their expense or revenue, and X is representing the number of lawns that Nate mows. So if our money that we have to spend is $2 per lawn for gas, so 2 times X, plus the initial value of $200 for a lawnmower. Nate's revenue is going to be $25 per lawn. It is a proportional relationship, so there's no y-intercept. Here's our 2 equations we're going to use. So let's compute. The first thing we're going to do is substitute y in one of the equations. This equation, the proportional one, is the easiest one to substitute, but basically you're just making them equal to each other. So we're going to go ahead and do that and solve, and he found out that it's about 8.7. Now, because this has context to it and it's not just 2 random equations, we're going to interpret this and make it make sense in this real world situation. So since X is the number of lawns Nate mows, we found that he needs to mow 8.7 lawns before his expenses and revenue are equal. However, Nate doesn't really mow partial lawns. He mows whole lawns. So we would have to round this number up and say that he needs to mow 9 lawns before he starts to have an expense and revenue equality, and before his revenue starts to become more than his expenses. So that is the information there. Nate will need to mow 9 lawns before his revenue exceeds his expenses. And the last problem you're going to try is this one right here. It's again on page 81 of your student companion. You have a Fun Time amusement park that charges $12.50 for admission and then 75 cents per ride, and River's Edge Park that charges $18.50 for admission but only 50 cents per ride. And we want to know for what number of rides is the cost the same at both parks. You're going to have to write 2 equations for this using the information from the word problem, and then using substitution solve.